This conference will now be recorded.
All right, guys. So, what we are going to come up and see today is time complexity analysis for your algorithms, right? So, why do we need this algorithmic analysis, right? Or what is the main, reason behind this? So, the main reason behind this is that we are trying to analyze three things. One is the worst case, one is the best case, and another one is the average case. So for your time complexity analysis, right, why we need it? We need it for an algorithm. We need it for an algorithm to understand in some simplified manner the below, right? So we need to understand what can be the worst case, what can be the best case, what can be the average case. Taking up to these parameters, we may try to optimize our algorithm or try to change the algorithm as well, right? So we may optimize algo or change the same in case our above expectations are not met. Now, when I'm talking about this worst case, best case, and the average cases, right? So, we are going to have this simplified manner. So, when I'm using this term called simplified manner, I'm trying to work on something known as notations for these cases. So, we'd like to work on notations for these cases. And one of the very, you can say, is known as this big O, right? So this is how we represented it as a big O, right? So this is one of the notations. Then other notations are also there. We got omega, we got theta, we got little omega, and so on and so forth. So let us try to see, first of all, right, what are the various notations which are available for us. All right, so this is a very quick introduction once again, right? So what is this time complexity analysis all about? Now what am I going to do here? So guys, let us import matplotlib. So I'll just quickly install this. I hope everyone is aware about the matplot. Right, so this matplot we would have done it right here and there somewhere, not in the data structure session. So this is usually to plot your libraries, sorry, to graphs. This is a library to plot your graphs. So I'm gonna go to these preferences. Let us come here and say matplotlib. So let me just fetch this information first. So this is the official matplotlib, right? A library package. So I'll just go ahead with the installation. So it will just take a moment or so to install the library. Let's just wait for the installation to finish.
This conference will now be
All
recorded.
right, so this installation is done. Now I'm going to consider this import first of all. So we say import. Let's just wait for this processing to get finished, right? So it's kind of updating the skeletons and the indexes, so just give us a moment. All right, so let us say import matplotlib dot pyplot as the plot, right? So I'm going to draw one graph here. So I'm considering that there is x with the input as 1, 2, 3, 4, and 5, and so is this guy y, right? So what is the relationship between x and y? Relationship is linear between x and y, right? So we have this relationship as linear. So I'm going to come up here and say plot dot plot. So let us say x comma y. So you are going to do a very small plotting here on x and y. So I can say plot dot, let's say the x label. So I'm saying the x label is going to be input, which is this guy called x, right? So I'm considering that your x is going to be input. So we'll write down it as input. This y label for us is going to be some time, right? So for one input, we take some 1 unit of time. For two inputs, we're gonna take 2 unit of time. Three inputs, we're gonna take 3 units of time. All right. So n inputs, we're gonna take n units of time. So this is how we are trying to understand this complete relationship. So let us say plot dot show. So when we run this program here, so this is time and this is input, right? So I'll just save this graph at the same time. Let us say linear. I'm just gonna save it with time complexity. So I hope this is clear, right? Now there may be some algorithm, right? So which will take one input, run for 1 unit of time. Let me try to give you an example on the same, right? So how this can come up, right? So this is majorly when you're trying to run a loop. Basically, when you go through a loop, right? Then this is majorly a case. Now, for an example, I say that I want to compute sum of first 10 numbers, right? So for I in range of 1 to 11, right? So there is some guy called sum, which is 0. So we say sum plus assign the I. Now, this loop is going to be executed for 10 times from 1 to 10, right? So if I will find the sum of first 10 numbers, so this loop will run 10 times, right? So we'll consider that, okay, sum assign sum plus I is going to do 1 unit of time operation. So there will be 10 units of time which will be clocked here. So if this is going to be your 100, so this is going to be 100 as well. So whatever is the number of, the elements which you want to add up together, right? That's like your n. That's gonna be your number of times the loop's gonna clock. So this kind of relationship is known as linear, right? As in the time will be consumed based upon the number of inputs which you are going to have. So it is always, the plotting is always between your input and the time, right? So let us now open the graph. So this is your graph, right? And I'm just going to open the paint. And this is our graph, right? So this one was your original graph, right? And this I'm going to now edit a bit. So how will this time complexity work? We know that this is going to take a linear time. So typically this is referred to as order of n. So we say this is big O of n. And we always consider that big O of n is going to be kind of an average case for us. Not the best case, but the average case, right? So this is a kind of an average which we are expecting. Sorry, my bad. So this I'm going to consider as theta of n. So I don't have this somehow theta over here. So I'll just draw it for you guys. So this is going to be your theta of n. So just consider this part over here. All right, I think we have a query coming in. Okay, so Lavish says why? So Lavish, because A is A. So this is considered to be theta of n, right? So what we're trying to say is that there is some program, some algorithm which is going to take linear time. So we consider it to be theta of n, all right? So you're understanding these bigger notations, various bigger notations here. Now there may be something, right, which is taking less time than this fellow. Now assume that there is some graph, there is some algorithm which is going to take a bit lesser time. So we'll try to draw it here. So this guy is going to take a lesser time for us. If you see now, right, this graph over here, this green line is obviously, as the input size increases, it's gonna take less time as compared to this fellow. There may be someone, as the input increases, this guy will take more time. So there are three cases for any of your algorithmic analysis now, right? When you're writing a program, as the input increases, the time will not significantly increase as in the linear part, right? So there may be a case this will take more time. So we definitely understand that this guy is going to be a slower algorithm and this guy is going to be a faster algorithm. Can I get an acknowledgement? Right. So we consider that there is an average case which is always a linear model theta of n, right? It's an average case. So what we consider that if there is something known as, you know, kind of something with respect to theta until the fastest one, right? So if I consider this region here, so if I'm going to consider this region here, this angle over here for us, right? Just give me a moment. So this entire portion for us is considered as big O of n. So I'm just gonna write it for you once again. So this is going to be your big O of n. In case we start from here, right? We start exactly from here and till this part here, right? So this entire belt forms the big O. So we are looking forward for the big O part, right? As in if it is same as in theta of n, or it is faster. Now there is another part for us, right? So which is what? Which is this fellow. The other part for us is this guy. So this entire region for us is considered to be omega. So either same or less than this guy same, right? So this omega. So guys, this is your omega of n. So there are three cases which we always need to understand. Can I get a smiley as an acknowledgement here? What is what basically? Now, anytime you will be working on your algorithms, so there will be something in this manner which you will get by solving your instructions mathematically. Of course, whenever we have to come up and solve the problem statement, right, we'll write this kind of a code for us. For example, here you have written a code. This is one code here, right? So we understand that, okay, this statement, the for loop is going to run n times, whereas sum assign sum plus I will do only will take only 1 unit of time. This we already have seen, right? Now from the graphs, right, we understand what is what. Now in case we don't touch down the theta of n line, we say it is only slow or only fast, right? Then we have some more terminologies linked with us, right? So there is something known as small o. So we even have this guy called small o, and we have this little omega. So these guys are not going to touch down to this, right? So they are still here, but they don't touch it. Same way, this guy will not touch this guy over here. It's not going to touch down, but it is less. What I'm trying to come up and summarize this for, that there is something known as big O, right? So we write it like this, O. So this is the general notation. This guy says that I'm going to be from ideal, right, till fastest. So this is what I'm going to tell you. All right. So when it comes theta, so this guy says that I'm going to be one ideal, right? Right. So when I say ideal, it is kind of a same rate of growth. So as the input increases, the time increases. It's kind of linear for us, right? So theta. Then we do have something known as omega. So omega is the guy which is supposed to come up and tell us, right? Either I will operate from ideal till slowest. So for the big O, we got this guy called little o. So this guy says not from ideal and till fastest. Same way we have this guy called little omega. So this guy says not from ideal and till slowest. Guys, can I get an acknowledgement from all of you? Are we good to go here? So what are these and how we can always understand the part of analysis? I hope this part is clear to everyone. Great. So when we are going to analyze our algorithms, right? So there are few rules which you should follow in order to understand where what will lie, so you can very easily now analyze. So as per the rules, you always tend to ignore constants, right? So if there is some algorithm which is going to take linear time, right, that's like order of n, right? This is a linear time. So there may be that you computed something like now for an instance, right, the output for your mathematical analysis came up like 5 times the n, right? So this is nothing, this is order of n. We are going to ignore this constant here, right? So there is something known as rule of domination. Now you can say dominance. So your order of 1 means it is going to take constant unit of time, which is less than order of log n. So we'll see what is meant by log n, because this is a general term which is considered. So order of n, I hope is clear to everyone. So order of 1 means only a one instruction. For example, you're going to solve an equation y is equal to let's say some mx plus c, only one equation you're going to solve. Then you got order of n square. So this is generally what we have. Then you have something like your order of 2 power n. So this is exponential basically. And there may be a case that we land up into something known as n factorial, right? So for example, you're trying to solve the Fibonacci problem, right, recursively. So guys, this is the rule of dominance. It means what? If your algorithm has some instructions which will take order of 1 time, but due to any instruction you are going to take order of log n, so you choose order of log n as the time complexity, right? So in case my algo is going to take uh, constant time for few instructions and log n time for another few instructions, so we will choose order of log n as a time complexity. Very important concern here to be discussed, right, in a way of what is meant by this rule of dominance, right? Now when I'm saying rule of dominance, so I'm just going to give you an example. There is a case, in case your input is greater than 0, so you do some operation and this operation takes order of 1. You do some operation, right? There is some operation which you are doing. Then there is something like elif your x is less than 0. So this is another use case. So your algorithm is going to work and now it is going to come up here and say that okay, this is going to give us some order of log n, and then I'm going to come up here and say an else case here which says that this guy will take some order of n square. So typically what we are understanding is that you have some different instructions written here, here and here, which will give you different results. All right. Now when your functions are supposed to be measured, right, we understand that x greater than 0, we got the best case, right? Then let us make it more simplified. Let it be x order of n. X less than 0 is going to take some linear time, which we consider as ideal time. And the else case is n square. It means it's gonna take a lot of time, which is the worst case, right? So you have this bigger notation. If you just refer it to your graph here, right, your bigger notation, if something is going beyond this ideal, beyond the theta, into the range of omega, this is not good for us. If it is something on the theta lines, right, it is considered to be as average. And if it is something less than this, so it is considered to be as very wonderful, right, the fast part. So your big O is the only one notation. The other notations are just for your referral purposes, right? You can obviously use them for very micro level analysis if you want anytime in your life here and there. But we'll just have this bigger notation which is going to work for us. Now, for this kind of, for above kind of solution, we have only, we have time complexity as order of n square, right? So this is going to be our time complexity. Now, there may be a case that x greater than 0, you are writing something like x assign, let's say, x plus 10, right? Or let's say x multiplied by 2 plus the 10. So there may be case here that you are going to come up and do something with respect to a for loop for I in range 1 to 10, right? You're going to say x plus assign, so x multiplied by 2 or x multiplied by I plus 10. Yeah, that's it, right? For example, you're going to do this kind of an operation. Now there may be an else case that you have a loop here for I in range. Let's say this is going to be something like your 1 to 10, and for j in range 1 to 5, right? So you have certain kind of structure. So here what you're going to do is, here you are trying to say x is your I plus j. So x plus a sign, maybe I multiplied by j, for an example, right? Now this is an example of order of n square. So for your entire algorithm, even you do have these different cases, but the case to be understood is what, right? The case to be understood is what is the worst part for our algo. So the worst part for our algo to be considered is this graph where we go into the range of omegas, right? So when we say worst part of our algo, it is order of n square. So the time complexity analysis, in the time complexity analysis, we do not care about the best cases or the average cases. We always care about the worst cases. Why we care about the worst cases? Because the worst case is the one, right, where you end up in making your customers suffer at the end of the day. Lavish, big O is not the worst case, right? So big O notation is to tell you about this section. Omega is to tell about this section, and theta is to tell about this section. But generally, in computer science, what we do is we don't tend to come here and write this as theta and omega. Okay, so what we do is we only write big O, but we understand that this guy lies in the range of omega. That is what we are trying to understand from the graph itself, right? So in general terms, we'll use big O. To represent any algorithm, you use big O, right? This is going to give you the analysis of your algorithm, and thereafter you understand, okay, that this guy will lie in this range or in that range. So good to go, Lavish. That is indeed a question to ask, no doubt about the fact. So can I get an acknowledgement from all of you? All right, so coming up with the same example now. So this was one part, right? So let us once again import the matplotlib dot. Just give me a moment here. I'm going to write this Python file session number 41A. So coming here and I'm writing this thing. So let us consider your x1 as, or let's say x is 1, 2, 3, 4, and 5. And y is also the same. Y1 is same, and we got something known as y2. So which I'm going to say 1, 4, 9, 16, and 25. Right, guys? So this is what I'm going to consider as two different things here. Now let us come here and say plot dot plot. So I'm gonna plot x with the y1, right? And I'm considering this dash, and then I'm gonna consider your x with the y2. For this, I'm just gonna say something like bs. Now, whatever I'm doing here, let me show you here. So let's say in a simple way, x comma y1 and x comma y2, and I'll say this plot dot show. So what we see is, right, so this orange line here over here is representing the n square, and this blue line over here for me is representing this n, right? So anytime whenever we are going to analyze some of our algorithms, right, so it's not that they're gonna take the same time, right? So this was just one connection to this previous discussion of what is meant by this order of n square, right? And if you want to come up and say this constant time, let us take it as y1, y2, and y3. So let this constant time be 5. For any input, you have the same output in the same manner, right? It's up to us, right? Whatever we want, we can take that. So y1, y2, and the y3. So you see, this is the constant time. This is your linear time coming up. The orange line is your linear time, and this green line over here is coming as your order of n square. Can I get a smiley? What is what? Basically, just for your referral purpose, guys. All right, so let us proceed and now try to understand a few more things. So in the time complexity analysis, right, so you'll always end up in evaluating some series more or less, right? They will end up in creating some of the solutions for you. Let us try to understand something known as logs. Whenever you understand logs, right, you kind of understand the complexities in a very better way. So there is something known as log of 8. In general notation, right, when I'm considering the logs, right, we either tend to take bases as 2 or 10, right? So bases are 2 or 10 generally. In computer science, since you deal with binary, right, so we always prefer base 2. So what does it mean now? So for log 8, right, understand that 2 power 3 is going to be 8. So if I say this log 8 to the base 2, so the base is 2, right? So this is going to be a general solution. This is going to be a general solution which says 2 power 3 is 8. So what exactly this means now, right? This means that the initial value was 8, then you divided it by 2. So thereafter you got something known as 4. Then you divide it again by 2, you got 2, and again you divide it by 2, you got 1. So when I'm using this logarithmic thing here in our discussion, right, we understand that 8 is being divided by 2 again and again. So can I get a smiley here? All right. Now consider that you're going to solve a problem, right, in this manner that there will be a tree kind of a structure which will be created. So you'll have nodes, right? So I'm considering that there is some node. So we'll say that this is one node here, and you have this left node and the right node. So I'll just put it like this only, right? So you have this left node and the right node. Then again, you have these left nodes and the right nodes. So here we are, right? And this guy again is going to have few more nodes here associated with it, right? So if you will observe, there is a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So how many nodes are there? So there are kind of 9 nodes for us. So there is some problem, right? Consider that there is some problem. There is an array which is initially like some data 1, 3, 5, 7, 9, maybe some something like this 11 and 2, right? And let's take one more number, let's say 8. So you have this in a list, right? And you want to divide it into two parts. So you divide it into two parts, 1, 3, 11 and 8. Then you got another guy called 5, 7, 9 and 2. Then again you divided this fellow into two parts, 1, 3 and then 11 and 8. And this guy also got divided into two parts, 5 and 7, 9 and 2. And lastly what you did, you again further divided. So you got 1, 3. So 1 and 3 we got from here, and then 11 and 8 you got from here. Then same way you got this 5 and 7 here. Then you got this 9 and 2 here. So anytime when you are working over these kind of problems, right? When you have this tree kind of a structure, so there are some levels which are being formed, right? If you see, this is going to be your level of 0. This is going to be your level of 1. This is level 2, and this is your level 3, right? So there will be levels, and we know that there are total of 4 levels. So these are 4 levels in total. We have a proven mathematical formula, right? So you can say 1 plus floor of your log of 9. So when I'm saying 9 here, right? So 9 is kind of your number of nodes here, right? Since nodes were 9 here, right? So log of 9 will come up somewhere around 3.17. So 1 plus floor of 3.17. So you consider the floor value. So it's going to be 1 plus 3. So you're going to get this value as 2. This is a mathematical proven formula that you will have these 4 levels coming up, right, in case you have 9 nodes. So typically, when we are going to solve the problem in a certain way, right? So you have these levels 0, 1, 2, and the 3. There are 4 levels, right? So there are some 4 levels in total. So whenever you have these levels coming up, this is basically taken care by your logarithmic approach. So you need to understand that how the certain things are going to work for us. So guys, can I get a smiley here? So if you see here in this, so you have n as 8. So there are 8 numbers for us, right? And this is what basically this is log of 8 sine 3. So basically you are going to divide your array 8, 4, 2, 1, right? So if you see this, this is how the structure is going to be for us, 8, 4, 2, 1. Anyone finding any challenge here can please raise the same, guys. Is this part clear to everyone? So guys, please raise the queries in case you have a query here. So where exactly you are stuck. So I'll take one more example here. So for this array, right, and if you are trying to come up and see, we will take up the same use case. So the initial size is 8. Then what you did, your array got divided into 4 and 4. Then here your array got divided into 2 and 2. And then lastly your array got divided into 1 and 1. So this is how the general things has happened for us, right? So what we understand is that this guy is your node, which is only one node. To begin with, you have only one node. That's like your 2 power 0. So here you got 2 nodes. So this is going to be 2 power 1. This is going to be 4 nodes. So this goes like your 2 power 2. And here you get this guy called 2 power 3. So Lavish, good to go here. Now is this clear, Lavish? Right. So Lavish, this is a mathematical formula, right? So how you can evaluate levels in any let's say binary search tree. in the BST, how you can come up and get the level. So this is an equation, a derivation which has been proved. So 1 plus floor of log n, where n is the number of nodes, right? All right. So guys, it means that if you're trying to do merge sort, right? You're trying to do merge sort. So we do it in the same way. You do divide and conquer, you do binary search. So you can come up very easily and detect that where are your logarithmic, kind of models coming in. So I hope this is clear to everyone, right? What is big O, what is theta, what is omega, but you always consider your notations to be represented with big O. So this is going to be big O of log n. So your merge sort, your binary search, etc., where you divide the problems by 2, right? So this is going to be your order of log n. And when we are trying to come up and represent this, it is with big O. So it's not considered to be as okay that we are going to represent it as theta or omega. Okay. So big O of log n, we are always trying to represent. So we are trying to represent, this is the worst case for our algo. You need to understand, even the worst case lies in the range of your omega, right? But we have only one guy in computer science through which we are going to do this representation. That's like your order. So big O order. So it's in the order of log n, right? The worst. So the best will be obviously you have only one node, right, or two nodes. So it's gonna take lesser time. But this is how you try to evaluate the worst time and you represent it with the order. So this I'm going to push. So what you need to do is you need to come up and give me the time complexity analysis for the Prim's algorithm. So I don't know how many of you have solved the Prim's algorithm. So I'll just put up here. Solve and compute time complexity analysis for Prim's algorithm. All right, so this is going to be the assignment. So the next part of our discussion may be the queries, right? That's what we are left with now. So in case you have queries, you can post it in the WhatsApp group, right? I will take up from there and we'll see and we'll plan the session and accordingly we'll proceed, guys. Okay. All right, guys. So this is all from me for the day. So thank you so very much. So see ya tomorrow, right? And please try to first of all put up your queries and thereafter we'll plan the session, right? I need to just see what and all queries you guys have. Accordingly, we'll plan the session. Because if the queries are more, right, I may plan the session for a longer duration on some other timestamp. Thank you so very much. Have a wonderful time ahead, guys. Bye bye. Thank you.